Okay, let's get started. First off, thanks very much for taking some time to attend this session. We're super excited to share some information about scheduling on Amazon ECS. Do a quick deep dive into how it works, some of the primitives that we've built that we feel enable customers to operate and manage containers at scale. And then we've got some, I'm going to do the dry stuff. I just shared this with Shuba and Matt. And then we're going to get them up here talking about real-world use cases that are super cool, how customers are building on ECS today. Matt's joined us from Expedia, and Shuba, who will follow him, is a senior product manager on our team working on the Amazon ECS product. So my name's Anthony. I run the product and engineering teams for ECS and ECR, and let's just jump right into the topic. So first off, when we think about containers, really what Docker has done, providing a mechanism for packaging, distribution, and for the portability, right, of containers. This is something that really changed the landscape. And when we started working with Docker several years back, we realized, in talking to our customers who were running Docker containers on EC2, that running one container was actually fairly simple. They started on their laptop, did some local development, figured out how to package up their application, and then as they started figuring out how to scale that, how to then move more to maybe a microservices model where they were breaking up these monolithic applications into components. They went from having 1, 10, hundreds to thousands of containers that now made up the different services across their infrastructure. And that really changed the landscape, right? You went from something that was really attractive, the portability, the manageability of what Docker gave customers, and then it became, at scale, really complex. You had to think about the problem differently. You had to think about how to keep track of all the containers that were running across your infrastructure. What happened if a container failed, right? It raised new problems. All of a sudden, now you had to think about how to maximize the utilization of all your infrastructure, all those nodes. Were they properly utilized as you move to this sort of new distribution model and running containers? And so that really was the primitives that we considered and the problems that we were trying to solve when we decided to build Amazon ECS back in 2014. And our commitment, as we thought through this problem for our customers, and as we engaged customers and said, how can we help? They had taken their applications and the way that they were running them, then they started to have to run all the side infrastructure in order to do this at scale. They had to run things like their own schedulers. Maybe they were using Mesos or Marathon. They had to keep track of the state. So they were running things like Zookeeper or etcd. And this was infrastructure that was not necessarily familiar with them. They hadn't necessarily had to do that before, right? They were running their applications on virtual machines, and it was a pretty well-defined and solved problem. And so our goal in building ECS was to remove that heavy lifting. We wanted to give a service or a set of services, APIs to customers to manage the life cycle of running containers in the cloud. And so that's where we started. We established a set of goals for ourselves that really evolved around security, scalability, and performance. Like those were some things that we wanted to commit to customers and give them as guarantees that if they chose to run containers on top of AWS, they would get those guarantees as they went and started scaling out and committing to this new application model. And what we've seen is customers love containers. We love containers. And today, that infrastructure that we showed, what we were building, is really supporting massive scale. We're launching hundreds of millions of containers each week on behalf of customers across clusters with millions of container instances. So really, it was important for us to get that underlying architecture correct and to think about how we could help customers solve the management process of those containers. So we kind of broke this into three key areas. This is kind of how we think about it. We might think about this a little bit differently. Schedulers mean a lot of different things depending on the technology or the stack that you use. But for us, we think about these as with three real key components. The first is a scheduling engine. The second is a placement engine. And then the third piece is really about the extensions or extensibility that you get, how you can build on top of that stack for custom schedulers, custom workflows, or be able to build UIs on top of your cluster state. So let's talk first just about the scheduling engine. From our perspective, the scheduling engine's role is just to start the task. So let me define what that term is for folks that have used ECS. A task is really just a group of containers. So if you have 3, 4, 5, 10 containers that make up your application, we give you a logical unit that we call a task that runs all those containers together. And then when we schedule that task for you, we make sure that all those containers are running on the same instance, right? So that's how we give you that guarantee. You define your task in what we call task definition. It's a declarative way where you say, here's the CPU, the memory, the ports, the container image that I need for this application to work, or container images if you have multiple. And you store that task definition with our service, and when you start the task, you specify the task definition that you want to start, and that's exactly how we get the tasks running in the right way. So some of the core underlying parts of the scheduler. But really, the primary role of the scheduling engine is to actually make the calls to the control plane, our control plane that starts the task on the specific node that's been identified. So who does the work to determine the most optimal place to start that task? Well, that's our placement engine. And we'll talk a little bit about that and how that works after we get through the different types of schedulers that we're offering to you. So we want to give you choice, right? So as you have different types of applications, they have different types of requirements. So we have 4 different types of schedulers that we think about. The first is a service scheduler. And really the role of the service scheduler is you tell us the task that you want to run, how many copies of that task you want to run, and that has a lot to do with scaling, right? And you can integrate this back into auto-scaling groups, right, and load balancers. So you basically model out how you want these tasks to run on top of your EC2 instances, and that comes in a service definition. And what we do with our service scheduler is if you say, I need 10 of these running at any given time, or 100, or 1,000, is that we're constantly monitoring the health of every single one of those tasks that are running across your instances. And if one fails, or 10 fail for whatever reason, whether it's a Docker runtime or out of memory on the instance, whatever it might be, we go and start another task for you. And if a node becomes unhealthy, and that node fails, and we have the auto-scaling group, we can go start another instance for you and then start a task for you if we have to. Right? So that really, the service is an important construct when we think about scheduling, because it's really sort of the start it and forget it, because you've got all the functionality for us to maintain and do all the heavy lifting for you to keep that service up and running. And we expose a lot of metrics and health checks out of that service for you so that you can go into our console or look at CloudWatch metrics or things of that nature to kind of get a sense of how your service is actually functioning. The second type of workload that we support with our schedulers are batch type workloads. So we've got integration with things like Spot Fleet. We allow you to use your own RIs with your ECS cluster, within your ECS cluster. And we support both long-running and short-running jobs. So there's no limit. You can actually run a task for just a few seconds if you want to. So we have customers that use that plus the Spot Fleet market and actually only run these jobs when it's optimal based off cost or time when they want that job to complete. We've also built a service entirely on top of ECS called AWS Batch, which gives you a nice friendly UI and job queues so that you can run millions of these tasks or workloads at any given point, and we actually make all the decisions for you based off the criteria that you set. The third scheduler is an evented scheduler. Super important, maybe you just want to schedule a workload to run, maybe it's once every day or once a month, some sort of processing. We do this based off CloudWatch events, so you can actually set triggers. If this event happens, start up a task, or on a schedule, start up a task. And so this is an important use case that we wanted to solve as well. And the fourth one is a daemon scheduler. What a daemon scheduler does is it's responsible for making sure within your cluster that a specific task, perhaps a monitoring agent or a logging agent, is running at all times on each node within your cluster. as your cluster scales up, it's responsible for understanding that there are new nodes entering into the cluster and ensuring that that task is running. You want to make sure, generally, that those logging or monitoring agents start up before any other tasks land on it. So it also has to take into consideration things like preemption or prioritization to make sure that there's resources on the node before any other tasks start up. We're currently working on the daemon scheduler, and we're doing that under our open source scheduling framework called Blocks. You might have heard us talk about Blocks a year ago. And what we've done, if you followed along the project, what we heard from customers is, first, we really like the idea of you open sourcing your schedulers, because that's like really close to our business logic. And if we want to have some sort of custom workflows, it'd be really great to be able to integrate this into the ECS schedulers. And we said, sure, yeah, that makes a ton of sense to us, right? We want to open source that entire stack. The next thing we heard is, but at the same time, even though we might want to run these on our own, if we have to kind of fork this and insert some different capabilities that are unique to our business, we really don't want to manage these, right? We really like the fact that we're able to use ECS and the APIs you give us to not have to manage any of the infrastructure, which also made a lot of sense to us. And so what we've done is built a framework for open sourcing our schedulers, and all of our new schedulers will all be open source under Blocks. They'll be available on GitHub. You'll be able to run them on your own, contribute to them, and the same schedulers that we build under the Blocks framework will be the same schedulers that are actually running in ECS. So why is that important? Well, let's say you have a capability that you want added into the scheduler, and you open up a pull request. We're able to vet it, make sure that it makes sense for the broad community, or we can implement it in a way that solves your use case at the scale, and we'll work with you on that, right? Make sure that we can operate that at scale. Eventually, that feature and capability make it into our control plane. It'll actually be running as part of the ECS control plane. And then you won't even have to run your own version of this. You'll actually just start being able to call the ECS APIs. So we're really excited about that life cycle and being able to open this aspect of ECS up to the community. So I've got some links up there if you want to follow along. There's a GitHub page and our Blocks page. Take a look at the project. The daemon scheduler and the design and the work that we're doing at that is currently available. So take a look and follow along for progress. Now let's jump a little bit into the placement engine. So this is the second core component that we wanted to expose to customers. What we do when you have an instance join your ECS cluster is we make important metadata information about the instances or the nodes running in your cluster available to you. So that's everything from AMI ID, availability zone, the instance type, and then we also added capabilities where you can create a custom tag. So you can say, these instances that I just added, maybe they have a specific resource. Maybe they're got a GPU. Or maybe you've launched a larger instance that has more networking bandwidth, and you might want to identify those for specific placement constraints in the future. You might want to do something around blue-green deployments and say, these here are for my blue set of deployments, this is for my green, or my development and prod. So you really can do a lot of things with the custom attributes and the placement groups that we provide as part of that. So once you understand the different metadata that's exposed to you, you can start making decisions about how to run workloads on top of your underlying cluster resources. And I want to talk a little bit about how that decision process is made. So the first thing, you can almost think about this as a funnel, right? And so at the top, you might have 100 instances or 1,000 instances available in your cluster. And as we analyze your request, we try and find the best fit, right? So it might be on if you ask for a bin packing algorithm, for example, like how do we make sure that we're honoring that request and packing as dense as we can on the instances before we start utilizing new ones, right? Or if it's spread these tasks across availability zones, we have to go make sure that enough of the instances to satisfy the request are in each zone for you. So first, we look at the hardware requirements of you, the CPU, the memory, the ports that you've asked us for. We might take that number of 100 instances, maybe it goes down to 50 that actually fit the requirements you asked for. Then we look at the custom constraints that you've given us. So that could be anything from the zones, or maybe it's an AMI ID. Maybe you have a custom AMI ID in this workload. Maybe it's a compliance type workload. It has to run on a specific AMI. We then make sure that we only select the instance that fit those constraints as part of the placement workflow. Then we honor the algorithm around the bin packing or spread. We have support for a couple other different strategies, which I'll show you in a second. And And at the very end, we apply that filter, and maybe there's 10 instances left. Then we pass that back to our scheduling engine, so that's how we close the loop, and then the scheduler starts the tasks appropriately on the instances that were selected. Here are the default strategies that we offer with ECS today. We talked a little bit about bin packing. We have spread or high availability scheduling. We have affinity. You might have 2 tasks that you really want to run together, or maybe you have 2 that never should run together for whatever reason. You want to make sure they're maybe for availability purposes, or maybe you want to make sure they're not sharing memory or something like that, right? Or 2 CPU-intensive workloads. You want to keep those apart, so you can do things like affinity or anti-affinity in your placement. And then we have something called distinct instances. So this is the foundational premise of a daemon scheduler, which is I need one of these to always be running, then I have to spread these across multiple instances. I really like this feature. I think it's super powerful, is we also support what we call strategy chaining. So in real world, you might actually want high availability, like I don't think we always do. We want our tasks to stay up and our services to stay running. But at the same time, we're cost conscious. So we might create a strategy where we say, run these tasks and bin pack them across availability zones. So we'll run them across the 3 availability zones where your instances are located, but within each zone, we'll bin pack them so you get the most cost optimal solution. All these default strategies are also available right in the console. So you can actually just go to the console and choose a default strategy, trying to make it super simple to get started. And we'll also let you, in the console, to customize this, right? So give us prioritization so that we understand what order you want us to, when we make that placement decision, what's the most important thing to you? Is it availability or is it bin packing? And then at that time, we'll apply even a custom strategy based off how you create your rules. This is just some visualization. We'll go through these quickly, and also to show you sort of how you can do this all from the command line. So you just run a task, choose a placement strategy. In this case, it's spread, and so we start those tasks across available instances in each of the availability zones. Here's the spread and bin pack, so you can visualize that within each availability zone, we're going to bin pack in an instance to drive up utilization for you, lower cost. And then we've built a multi-tenant scheduler, and all these scheduling options that we've talked about can all run on your single cluster at the same time, and that's kind of unique. And the value proposition there is that with one single cluster, you can actually run hundreds of services with all different types of placement strategy, and we'll find the best fit for each of those. Okay? So in this example, you have one service that you just want to keep bin packing, and so we're going to bin pack every time you scale. We'll always just take a single node and start bin packing until it's fully utilized. And then at the same time, we'll have another scheduler that's actually running a service that is making sure that we honor your availability requirements and spreading across nodes. So jumping into the extensibility, this is really important because as we talk to customers, we try and build these rich scheduling and placement functionality directly in the control plane. So again, like we can remove that heavy lifting from the customer, but at the same time, we know it's super important to help use all sorts of different use cases that customers might have. And so there's 2 things I wanted to share that we've done that I think are super powerful. The first is we've added a cluster query language. And what that lets you do is, from the API, you can make calls against your cluster, list container instances, and pass in, through a cluster query language, certain constraints. So you can say, tell me all the clusters in my, or tell me all the instances within my cluster that are of the T2 family. Or tell me all the instances that are running this specific AMI, right? Or tell me all the instances that are running this specific operating system, right? So lots of different things that you can choose, and then you'll get a return set of the instances that meet that criteria, and then you can actually have your own custom scheduler or own workflow that says, go start these tasks on there. And we have a start task API that you can use to target a specific container instance ID. And the second thing we did last year is we built an event stream. So it's one thing to pull the service and to get this information on, when you need it, but a lot of times we want to be a lot more reactive. We actually want an event to come to us to notify that something in our cluster has changed, the state has changed, and that there's an appropriate action that should take place as a result of that. And so the event stream lets you actually absorb task state changes and cluster state changes from your environments and filter for different types of events, whether it's a stopped instance, new instance added, stopped task. There's lots of different things you can filter on, and then you can build, again, custom schedulers, or we see a lot of people using this to keep real-time UIs of what's going on across their cluster. Right? And there's no polling, it's all, you don't have to worry about hitting throttles or limits or anything like that, because this is all event-driven. Like, we're just pushing events to you, and you consume them, and you can call this local cluster state that we give you as often as you need to. Okay, so the next part here, I want to invite Matt up, and what Matt's going to do is spend some time talking about how to use the primitives that I just went through in sort of a real-world scenario. Thanks, Matt.
Thanks, Anthony. My name is Matt Callanan, and I'm an engineering manager at Expedia. So I'm in the cloud acceleration team. We're a team that kind of sits between the AWS platform and our development teams, and we aim to speed up our development teams and how they get to the cloud, how they deploy. Out of our Brisbane, Australia office, where I'm from, we help to manage and maintain the automation around our ECS clusters. So today I want to talk about a specific use case of placement constraints that we found helps us when we automate the updates of production clusters. So when we talk about replacing all of the instances within a cluster, when we do maintenance, we have an immutable server approach that we take to maintaining our clusters. We never patch instances. If we want to make a change to an instance, we will build a new AMI and we'll roll that out to all instances in the cluster. Before I get into that, just some background about how we use ECS. So we have around 2,600 ECS services out there. That's made up of 1,100 unique applications. Internally, we have a microservice generation tool. Developers can go and click a button and generate a microservice, and they do that 20 times a day. So we've got 4,000 of these applications. We have around 860 EC2 instances in our fleets. We have 13 clusters in 5 different regions. Our biggest cluster in production is 230 instances. All up, we run about 13,000 containers. So we've done a lot of automation around how do we most effectively update those clusters. And one of the issues that we faced when replacing all the instances in a cluster was how do we make sure that the tasks that are being relocated from old instances to new instances don't go onto an instance that itself is about to be replaced, if that makes sense. So we want to make sure that when they get relocated, only go onto the new instances that we have there. So what we came up with was this idea of a placement constraint at deploy time that says when you deploy, only deploy to instances that are in this that are not in this state that we call pre-drain. So state is a custom attribute that we've created, and we only set that on instances at this cluster management, cluster update time. So let me show you what that looks like in pictures. So our cluster update process takes a CloudFormation stack with an auto-scaling group, which all of these 5 instances in this example will be connected to an ECS cluster. These are running 10 tasks. You can see service A there is running 2 tasks in that one service. What we do as part of our first phase of our update is we will duplicate the entire stack. So if this stack was 100 instances, we'll create a new stack, new auto-scaling group. Those 100 instances will start up immediately and join the exact same cluster. We double the capacity. And then what we're going to do is we're going to go through in batches in the old cluster, in the old stack, and we're going to go through batches maybe 50% of the cluster, and we want to drain those instances and start moving those tasks off there onto the new stack. Now at this point in time, we don't want those 6 tasks going onto the 2 other old instances that are still serving tasks and serving requests. We want to make sure that they only go into the new stack on the right-hand side. So that's where we've got this state attribute that we set on all of the 5 old instances. We say the state attribute for these instances only is pre-drain. There is no state attribute on those new instances. So we go through that training process. Those 6 tasks only relocate onto the new stack. And then we'll go through, wait for that draining process to finish, and we'll say, okay, the second batch also put that into draining mode, and they'll get relocated across to those new instances. And then phase 3 of our update process is to remove the old stack. It's something that we've come up with this year, a major project that we've had internally just to help with the idempotence, the rollback ability, the safety, the speed. We can do a full 100 instance cluster update in about half an hour. An important part of it is disabling and resuming auto-scaling processes as well. And this is what it looks like in the UI. We don't use the UI, we use automation with the SDK behind the scenes, but this is essentially what we say at deploy time. Make sure at deployment that you go to an instance that is either doesn't have the state attribute at all, or the state is only in pre-drain state. So it's a custom attribute, doesn't exist by default. Only set it during cluster update. Prevents ECS from scheduling tasks that are about to be drained, and we only ever remove it from an instance like that old stack if we had to do the rollback. If we had to reverse the process, then we would remove that pre-drain attribute, that state attribute, so that we could reverse the draining process back to the old instances. It's just a quick example, a quick use case of how we use the placement constraints. By default, we use AZ spread for our services as well. I'm going to hand off to Shubha now. He's going to talk about more use cases.
Are using scheduling tools, scheduling primitives that we just described. I'll cover what ECS does and how you can actually use ECS for linking it with the other triggers that you would like to rely on to scale up your applications. So first of all, you have an application, you're running some X tasks for that application. How do you know when do you want to scale it up? We give you primitives to actually trigger CloudWatch alarms based on how much CPU and how much memory your service is currently utilizing. And based on that, you can decide how many more instances of that service, that is tasks of that service, you want to spin up. And this is tightly integrated with CloudWatch. You can actually use the console workflow to set this up. It will automatically trigger more copies based on how much application load you're seeing for your service. So you know that for long-running services, what do you do for these services which don't really require to be running all the time? You could have some accounting, reporting, auditing applications which only need to come up based on some time schedule. And for that, we integrate with CloudWatch. So with CloudWatch, you can actually set a trigger either as a cron command or based on some primitives we expose in the console. And with that, the alarm will get triggered based on your requirement, and the task gets spun up based on that event. So essentially, we are making it easy for you to trigger spinning up your microservices only when you need it, and scale it down when you don't need it. That's the fundamental concept of how you can control what exactly you want to run at what point in time, based on your demand, based on your users. So it's not just about ECS. You could be using a lot of other Amazon services, and we want to make it easy for you to tie it with all other Amazon services as well. So we integrate with CloudWatch for every other service which can send events and triggers to CloudWatch. For example, your application may be seeing a lot of traffic, and your load balancing queues may be having longer queue lengths than you expect, or you may be seeing higher latencies. Or your SQS or SNS may be seeing higher than normal traffic and events. So you can actually tie ECS into any of these triggers and automatically scale up the tasks that you have in the service. Same way, we have some customers using Lambda. Based on an event, you trigger a Lambda function. The Lambda function puts something into a queue, like a SQS queue, and then you trigger an ECS task. The task comes up, reads from the queue, and then does whatever processing or whatever it needs to do. So essentially, we are making it simpler for you to cross-connect across AWS services. Thereby, you're scheduling your tasks and running your microservices only in a very easy manner. All these are reference architectures. You could look them up on GitHub. We give you a template to set all this up together. You're just changing with your task definitions and your image IDs, and then you're good to go. We have a lot of customers using ECS via the batch APIs. So AWS batch exposes primitives to have you specify jobs. Jobs actually take ECS tasks. They also let you specify where and how you want to run those tasks. We tie in with a lot of common workflow models, either Amazon or third-party tools, and help you do your batch processing on ECS in a very simple manner. So you could specify things like my job A depends on B, so only spin up job B after A is complete. Or for example, if there are a lot of our scientific and financial customers require jobs where there are multiple elements in each job and there are clear dependencies between each element in one job to each element on the other job. So this is new, introducing array jobs for batch. This helps you tie in all the specific entities in each of your jobs very tightly with the other entities in the other jobs. So, and we also have priorities. So some jobs may be more important than others. You may want to run some jobs with asking for an on-demand instance, and maybe you want to run some other jobs based on when a Spot instance becomes available. So we let you put your jobs into different priority queues and only run them based on your specific needs for that application and for the cost and the capacity that you want to provide for those applications. So with all this, you're making it easy. We are making it easy for you to run microservices. How do you do actual deployments? When you think about your application developers, how do you make it easy for them to really build applications, focus on your customers, and then push out all the code changes that they're constantly developing into ECS? So that's something we've worked on a lot in the last year, and we are introducing integration with code pipeline to simplify and automate continuous deployment to ECS. So what this means is that once you have a code repository, which a code pipeline understands, it could be either on code commit or on GitHub or any other partner which code pipeline works with. Once there is a code check-in, you can trigger automatically a pipeline that takes the new code changes, does all the testing and deployments. It compiles an image, pushes it to ECR, and deploys a new service on ECS. Again, code pipeline is very flexible. You can define your own release process. You can specify checkpoints, either a manual approval if you need it, or you can even specify different environments. How do you want to automate testing between environments and then failover or fallback if you see any errors in that. So with all this, it's easy for you to focus on your application and leave the heavy lifting of deploying your code onto ECS to us with all these integrations. So you have a new service and you want to deploy it, and code pipeline puts it on ECS. So what happens next? ECS gives you services which actually lets you specify the number of tasks, and we also do our deploying in a rolling manner. So let's take an example of a service where you have 4 tasks. We expose max and min attributes. Essentially, you can say how many maximum healthy tasks can you have for this service, and how many minimum do you want to keep up and running at any point in time. So for this service, if you say I want 4 tasks, I want all 4 of them to always be available, and I can actually spare some extra compute to make a deployment, in the sense that if you deploy the new version, and then ensure that it is running and healthy, and the load balancer is connecting to it and marks that task as healthy, only then spin up my existing task. That's something we can do for you very seamlessly without you having to do anything. Again, the same with an application where you may not really want to provide it more additional compute. You can specify, I want to keep my 75% of the attributes healthy. In that case, we do a rolling deployment. You'll have a new version of the task come up, and only then take down the old versions of the applications. So that works if you are OK with running only one version. What do you do if you want multiple versions and test them all before you actually switch over your application traffic? Blue-green deployment, we make it easy for you to deploy the canary in the coal mine, for you to deploy the green version and actually test it out in a weighted phased manner before spinning down the existing application. So this is a reference architecture we have on GitHub. We use Route 53 and weighted groups on Route 53. If your customers are, so it uses step functions behind the scenes to actually roll over traffic from the old version to the new version in a real gradual manner. So it gives you a visual workflow where you can see what percentage of the traffic is actually sent to the new version. You can see what all the metrics of how the new version is faring. And based on how happy and comfortable you are, you can actually either make it go faster or slower, or even just revert back to your existing stack. We also are introducing service discovery for ECS. So you have multiple services. How do each of them discover the new versions of the other services? This is something that we are working with Route 53 to solve. We have a concept called namespace. You can register all your services into a namespace and thereby have multiple versions of the services running in parallel. ECS scheduler does all the heavy lifting behind the scenes to make sure that the Route 53 service registry is always up to date. So with that, your clients can always do a DNS query, get the latest healthy endpoints, and then connect to them to get the latest version of other dependent services. I'll be speaking more about service discovery in my session on Friday, so feel free to attend. So all this is good for making sure that your new applications are up and running and they're connected with all the other dependent services. How do you manage where exactly it runs? So you need to, there are a couple of common patterns that our customers are using today. We have integration with Spot and auto-scaling. So Spot lets you bid for the instances that are additional capacity that you can get at a reduced price. We have integrated with Spot Fleet. Spot Fleet enables you to maintain the fixed number of CPUs or fixed number of instances at all points in time. And that does the work of ensuring the bidding process is going on behind the scenes to give you high availability as well. So Spot instances could be spread across availability zones, and it will automatically be configured to be a part of the cluster, which is the Spot Fleet cluster. So ECS integrates with Spot Fleet and runs your services on Spot when it's available. And this is something that you can leverage to either increase your compute capacity at the same cost or to run your services which are okay for being interrupted at lower prices. So how do we do this auto scaling? Essentially, so if you have developers who are building new applications, that's always good. If you have automated it all to go on a cluster which has a fixed capacity, then it may not really have the additional memory and CPU that's required to deploy your new applications. So, or if your application increases, if your service increases the number of tasks it's running, then how do you make sure that there is always compute capacity to handle that load? We integrate with auto-scaling groups with CloudWatch events. We send out events based on existing CPU and memory reservation, which means you're actually always optimizing for everything that a task or a service could potentially use. Or we also give metrics on actual usage. So that's how much it's exactly using despite how much it had reserved. You can tie that into an auto-scaling group, which automatically increases the size of the number of instances that are a part of the cluster, and then the schedulers will kick in to actually place them, place new tasks, or place the tasks that are pending, waiting for compute resources, into the new instances. So you have growing clusters. How do you collapse them? So we also give you metrics for utilization, which you can tie into a Lambda function and then spin down the number of instances that you have in the cluster if you're not using it. Again, we give you a flag called draining. This is going to help you simplify how we actually scale down. The Lambda function can set a flag called draining on an instance which is running low on utilization. Then what that triggers is that the ECS scheduler will be aware that it's an instance which is about to go down. So it will not place any new task on an instance which is in draining state. Also, if if your service allows the tasks to be placed in more than the number desired, essentially if the max healthy percentage is beyond 100, then ECS scheduler can also place new tasks and actively spin down the tasks that are on your draining instance. So with that, you can free up your instances that are going down. Essentially, your applications do not see any impact in terms of availability or latency because we are always ensuring that there are the desired number of tasks available for you on your behalf, behind the scenes doing all the training and the task placement adjustments as required. So all this will go away with the introduction of Fargate. You may have heard about it in keynote today. So we are making it easy for you to focus purely on your application and not worry about the instances that you need to provision to have these tasks and have your microservices always be easily deployed and always running. So we introduced Fargate with ECS. It'll make it easy for you to scale up your services or to scale down your services, directly thinking about containers as the primitive or tasks as the primitive without having to think about all the compute. The 4 previous slides where I spoke about patterns is not relevant anymore. Fargate is integrated with all the same integrations that ECS supports today. You can use AWS VPCs, you can get a task IP, you can use security groups, you can use load balancers, you can use CloudWatch, you can use it with all the other services that AWS has. It's fully managed by Amazon, so you're not really thinking about how many instances are there and how do you scale it up. We are doing it for you behind the scenes. And your service guarantees of how many tasks are running and how exactly are they placed across availability zones, that still is applicable. So the placement constraints that you give to spread it across AZs for having high availability, high reliability, that's still applicable. All the scheduling that we provide is still applicable, but you just don't have to think about bin packing to save costs or to really optimize for CPU memory reservations and stuff like that. So with that, you'll have more about Fargate in the upcoming sessions. Please attend them to really understand how exactly Fargate works. Thank you. This all we had. We can take